just want to show you that the calendar's been completely updated here. And here's when your finals are. And you see that this homework, you've probably already finished this homework. It was due yesterday, but one section hadn't quite caught up, so we extended the due date for that section, which means we extended it for everyone. So if you haven't done homework 23, you still have time. Now, homework 24, which covers what we're doing today on nonparametric tests, is posted. And so you can do it right after class, and it's just covers exactly what we're doing today. And this homework has not been posted yet, but this will be on what we do Thursday, and I'll post it right after class on Thursday. And this right here is now posted as well. This is your last R bonus assignment. So we're pretty much up to date, and we'll finish the book on Thursday, and then we'll have a review, and I'll post, right after this weekend, I'll post practice exams and how to study for the final, which is really just exam 3. It's a 90-minute exam. I say, look at this, I give you 3-hour time slot, but you're only going to really need 90 minutes. You have a 3-hour time slot because anybody who missed an exam with an excused absence, exam 1 or 2, will have makeups during the second half. So it's just like a regular hourly exam. Okay, any questions on that? All right, so let's go to the document camera and get started. So we're going to talk about in this last section, part 16, is nonparametric tests. All right, now we've done one other nonparametric test, which was the randomization test. But all the other tests, what is a parametric test and what is a nonparametric test? A parametric test assumes that your data comes from distributions that are defined by parameters. And we're estimating those parameters. For example, the chi-squared, the z, the t, the f, those all those tests have parameters associated with them, right? Normal curve has a mean and a variance, and that defines the normal curve. And so we estimate those parameters. Now, nonparametric tests, what are they? They don't make those assumptions about where the data comes from at all. They don't assume it comes from any kind of distribution that we, with a well-defined parametric description. And where does logistic regression fit in? Logistic regression doesn't assume normality, but it does assume that the data follows that S-shaped curve, which had 2 parameters associated with it once you put it into the log odds form. So that's basically what I say here. I say parametric tests are based on assumptions about distributions defined by parameters that we're going to estimate, that our data are sampled from. Most of the tests we've been doing, wait a sec, all except logistic regression. Assume that we're dealing with either normal populations, like the chi-squared and the z, or statistics that follow from normal distributions, like the t and the f. So, so these are, or that the central limit theorem kicks in, and our, our statistics that we're looking at, our test statistics, we have a big enough sample size that they'll follow a normal distribution. Okay, even if the data they come from isn't normal, the test statistics will be normal, like the mean, or the, for estimating means. All right, so now in part, our last part, part 13, right? We did data transformations. part 13. And we saw how we could sometimes transform data with lopsided histograms into data with more normal-looking histograms by either, like if we had distributions, well, this is the one we're more familiar with. If we had distributions with this long right-hand tail, we went, we went down the power ladder, like we tried to squeeze this part in to make it more normal by using logs, right, exponents, and we squeeze that in. Or if we had data that was left skewed, then we went up the power ladder, and we didn't do that as much. Okay, but what if we can't just, change the data into something more normal looking by doing this and using our regular parametric, our regular distributions? So then we have these two options that we can do. Is that clear? There are two options. All right, so these are two kinds of non-parametric tests. All right, we can either do what we've already done, right? So these are two types of what we call non-parametric tests that don't depend on those assumptions. So they're very useful. They're very robust, and they're being used all the time. So the first one that we looked at already was a re-randomization test. And we saw, what did we do? We let the computer create these empirical distributions by randomly sampling all possible samples under the null and seeing how likely it was to get our particular sample. So we have these empirical distributions, and they didn't depend on our usual assumptions about normality, the errors, and all that. So that was one thing. There's lots of these types of, this is called a permutation test as well, a re-randomization test. We're looking at all possible permutations and looking at their probabilities. It's one of a class of sort of resampling, called resampling re-randomization tests that include bootstrap, jackknife, Monte Carlo simulations. It's all part of that, using computer simulations to create these distributions. And so this is very, very widely used, and we just looked at one type of that. But then there's another whole different type of that we're going to look at in this section of non-parametric tests. What we do, we replace our actual values by ranks. So if you have whatever your sample size is, like if it was 20, it could have any numbers, 20, different numbers. What we do is we take those 20 numbers and we order them from the smallest to the largest and change them to ranks. So if there's 20 numbers, they're going to be changed from their actual values to the numbers 1 through 20, the smallest to the largest. The smallest will have the value 1, and the largest will have the value 20. And then we have this nice, very simple set of numbers, just integers between 1 and n. And we can then do statistics get test statistics on those numbers. And they're the advantage is that there's a lot of there's tables for those for integers 1 through n that will give you p-values very easily. And also, once your sample size is large enough, you'll have your uniform distribution between 1 and n. And so the sampling distribution of our statistics approach normality very quickly, and we can use, even with small samples, our z statistics. So that's, or chi-square statistics too. Okay, so that's the idea. And so this we did in, this was from part 13. And you're going to see so many different types of, these are all to get p-values. They don't give you parameter estimates with confidence intervals around them. These are to get to p-values. And they really help you understand what a p-value is. We saw that when we did the re-randomization test. And now, right now, what we're going to do is replace, let's highlight this as the key idea. We're going to replace the actual data, the values, with their ranks. That's what we're going to do here, okay? So, and then we've already done option 1, and now we're looking at option 2 and the rest of this lecture and the next one, okay? So we're going to look at, and the advantage of this second option, one of the advantages is that there's a few widely used non-parametric tests that are easily calculated and are available in most statistical software. And here's 3 of the most commonly used ones. All right, so these are the 3 we're going to be looking at. This we'll look at today, the Wilcoxon Mann-Whitney Ranksum test. And that's basically a non-parametric, it's analogous to which parametric test? To the 2-sample t-test. So it's a non-parametric version of the 2-sample t-test. What I mean is just you're looking at 2 small samples usually, although you could do it with large ones, and to see if basically they're the same. They come from the same distribution. And then there's this Chris-Cow-Wallace test, and that's the non-parametric version of our usual ANOVA to compare means. And the last one we're going to look at is a different way is the Spearman rank order correlation coefficient. Okay? And that's the non-parametric version of our regular correlation coefficient. All right. If you're interested, there's a summary right at the end. You can look at it right here. But these are these 3 non-parametric significance tests and their parametric equivalents here. So this is what we're going to be doing. And today we're just going to be doing this top one. This is on page 221. Okay? So that is the idea. So how does this work? So you have 2 groups, and you want to see if they're significant, if their distributions they come from are significantly different than each other. So you combine the 2 groups into one ordered list, and basically from smallest to largest, and you assign each observation a rank from 1 to n. Okay, so this just means what? Basically our first step is to change our values to integers between 1 and n, to ranks, ordered ranks. And then what do? Then our next step is we're going to compute this test statistic, which is the sum of the ranks. And so we'll compute something called the rank sum for each group. And then that's our test statistic. And then we're going to look at, from this test statistic, we'll see how it's distributed, and then get p-values from this under the null. Okay, so now, let's see. What did I say here? I said, I think this is pretty much covers it. With logistic regression, just to be clear, maybe I'm not all except, maybe I should say right here, put a little star here, that logistic regression is a parametric test, what we've been doing. With the logistic regression significance test, that's a parametric test. Why? Because even though we're not assuming normality, we're assuming we're assuming that our data follows an S-shaped curve. defined by two parameters, that it comes from data that, has defined by, we have a model that's defined by two parameters for simple logistic regression. Once you put it in the, what are the two parameters? They're just the intercept and the slope. Once you put it in log odds form, that's the intercept and slope. So that's certainly a parametric. All of them are. The other ones we did all assumed normality. This is the only one that didn't. Because all the other ones we did, we minimized this, all our errors were normal with zero average and the same variance, etc. And then we were estimating that variance. Okay, so I think you understand the idea here. Why don't we just do an example and you'll get it. All right, so two different forms of this is an example from real life that on our finals, we're really worried about making them the same level of difficulty. We have different versions, and we want to make them the same level of difficulty, and sometimes they're not. And so to really, we do a significance test generally before we give them. And what that is a lot of people take it early, the final, not a lot, but a handful of people take these finals early. And what we do, like let's say we had two finals, and this is taken approximately from one of our tests. So they're different, but we want to make sure, we're trying to make sure that they're the same, not just that they have the same mean, but they really are the same level of difficulty for everyone. So they basically come from the same distribution. So here's group A and group B. And let's say we have these are the scores of the two groups. Now, you might think, oh, why don't you just do a two-sample t-test? Well, we know that our exam scores aren't normal. They're never normal. So why not do, we have small samples from distributions with unknown standard deviations and mean. People haven't taken the test yet. Why not do a two-sample t-test? Because remember, one of the assumptions of the two-sample t-test is that they come, for small samples that you have a normal distribution that they come from and an unknown standard deviation, because we know that our exam scores are never normal in stat 100 and 200. They always look like this. You can see that. We have, they're capped at 100. You can't go over 100, and lots of people get A's and B's, and very few get way down here. That's a long tail. So this is a nice way to do this. So what do? So we change these numbers to ranks, okay? That's what we're going to do. So now what is the null hypothesis? The null hypothesis is stronger than the two. Another reason we do it is it's more what we're interested in. It's stronger than the two-sample t that just says the means are the same. There's no difference in difficulty between the two exams for any segment of the population. So this is stronger than just saying that the means are the same. It's saying what? It's the same as saying both groups come from the same distribution. Why is that important? Because we want to make sure that even if the means are the same, that it's not like much harder for like the low-end students, one of the exams, even though the overall means the same, or much harder, easier for the high end or whatever. We want to make sure it's fair for everyone who takes the test. It's basically from the same distribution. Okay, so, and the alternative is what? That they're not from the same, that the exam forms are not the same level of difficulty for at least one segment of the population. So they come from different distributions. Like one might be lopsided or something, even if they have the same, more lopsided than the other or something. Okay, so what do you do? So, as I said, change these to ranks. So how do we do that? All right, so we're just going to order them. So which is the smallest number? That's 1. What's the next smallest number? Here's 2. The next one is, this one is, if we put them in order, and then these two are tied. So what are we going to do? Combine the two groups into one ordered list. If there are any ties, give the average of the ranks. So for example, okay, so I have 1, 2, 3. I could say one's 4 and one's 5, but they're the same. So what we do is we take the average of 4 and 5 and get 4.5 for both of these. Okay, now the next one after 70 is here, so be careful. We did 4 and 5, so now we're at 6. Maybe the best thing to do is their numbers, there's 7 in this group, 8 in this group, so maybe you want to go up to from 1 to 15, and you can tell that's the highest one, okay? So that's 15. So now 1, 6, then what's the next one? Here, this is 7. Then we have, where is, did I do that right? This is 8, this is 9, and 10, right? 11, tell me if I make a mistake. At 12, 13, and 14. That's the second highest. Okay, so those are the ranks. All right, and now what do? We just sum up the ranks. All right, we're going to sum up the groups. Now choose one of the groups and add up its ranks. So here we're in step 2. This is called the rank sum. You may choose either group, but it's easier to choose the group with the smaller number of observations. This one has 7, this one has 8 observations. Okay, so let's add all this up. Oops, that's a plus sign. Just adding up all these numbers. And I added those all up, and I got the rank is 56.5, 56.5 for group A. Now, I really don't, once you get the rank for group A, rank B is determined because the two together have to add up to the sum of the numbers between 1 and n, right? And the sum of the numbers between 1 and m follows this nice formula here. So the formula says what? N is the overall number, which is 15 times 16 over 2. And this is 120. So this right here has to be 120 minus 56.5. But let's, we can also check that it is. So let's check that it is. So let's add this up. And when we add this up, I got 63.5. So what we're saying is 56.5 plus 63.5. These two right here have to sum to what? They have to sum to 120. So you check if they do. And they do. If you add them up, they sum to 120. So there's a nice story. One of my favorite stories about kid mathematicians was Gauss, who discovered this when he was a little kid in school. He was very fidgety, and Gauss, who the normal curve's named after. I mean, they call it the Gaussian curve as well as the normal curve. So very famous mathematician who was super smart, and but he wasn't a good student. His teacher would get mad at him and yell at him all the time. And so because he's so fidgety and just not paying attention, she said, okay, Gauss, you think you're so smart or something, add up the numbers between 1 and 100, and I'll take you the whole period, she thought. He thought for a few minutes and gave the answer. He said, 5,050. Everybody went, what? And you know how he did it? You've probably heard this story, but it's by this formula. Let's just do it with numbers 1 through 15, and you'll see what he did. So here's the numbers 1 through 15. So what did Gauss do? He says, okay, he imagined the numbers 1 through the highest one. Let's just write them down. Pretend it was 1 plus 2 plus 3 plus 4. Of course, he didn't write them all down. Plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14 and plus 15. Okay, so how are we going to do that really fast? So we saw, okay, well, 15 plus 1, n plus 1 is 16. So we thought, oh, 1 and 100 is 101. And he said, okay, we see 2 and 14 is also 16. So we said, oh, 2 and 99 is also 101. 3 and 13 is also 16. So he did this, and he realized, okay, so that's n plus 1. How many of those n plus 1s do I have? How many 16s do I have? Well, half the numbers. So it's n over 2. In his case, it was 100 over 2, which is 50, times 101. In our case, it's n over n plus 1 is 16, and we're doing it, we have an odd number, so if we kept going, it would be 16, 16, 16, 16, and then we have 1 in the middle, so that's n over 2, 7.5 times 16. So that works out, and if there was an even number, like in his case, if there's only 14 of them, then it would just be, half of them. You don't have to, So it's easy. Any questions? Did you ever hear that story before? Did you? Not? No, you did? Isn't that impressive? Because once you see it, it's really easy. But to think of it yourself is pretty amazing, So that's pretty cool. So that's what we're using here. And so we check. So I hope you remember it just by lining the numbers up and doing that if you forget the formula. So, let's see. So we can use a z-stat. Why are we using a z-stat? Since for large enough group sample sizes, these, people draw the cutoff at different places, but we're going to just say greater than 6. And in A and NB, they don't have to be the same. Here we have 7 and 8. The probability distribution of the rank sum is very close to normal when the null is true. And so these with expected value and the standard error below. So let's understand these expected values in standard error. So what is this? This right here is the expected value of the sum, all right? So remember the rank sum. So the expected value of the sum, as you know, is n times the average of the box, right? And average of the population. Well, that's all this is, right? The expected value of the rank A is n, which is its sample size, right here. That's the sample size. NA is the sample size for group A. Okay. And this right here is the average of all n numbers. So we're randomly, think about, what we're doing is we're saying under the null, we're saying that we have the numbers 1 through 15. And we're randomly taking 7 of them out and counting up their sum, whatever ranks we get. And the expected value is going to be n times the average of all 15 numbers. So this is the average of all n numbers. So in this case, n so we have n sub a, and then our average is going to be what? It's always going to be n plus 1 over 2. That's our average. So in this case, we have 7, 1, 2, 3, 4, 5, 6, 7 numbers. That's where that is. That's times. And then we have the average of all of them, which is 8. N plus 1 over 2, 16 over 2. 8 right in the middle. So that's what we'd expect, 56. Does that make sense? Wouldn't you expect, why would you expect, if you randomly divide them up, you're not going to expect all the low numbers in one group and all the high numbers in another. You're just going to say, okay, on the average, you're going to have the n times the average. Right? That's what we always would think. Wouldn't you think that? Okay. Does that make sense, people? So that's the expected value. And this is what we actually got. That's our observed value, and that's our expected value. So what are we going to do? We're going to do a z-statistic where we have our observed 56.5 minus our expected, right? That right there, which is a difference of 0.5 over some standard error. Now the standard error is this, and you probably look at this and say, why? First, let's just calculate it. So what is this? And it's the same for both groups because once, and that makes sense because it's determined. Once you know this expected value, you know the other one, and they're going to have the same standard error here. So it's what? So this works out to be NA 7 times 8, which is the same 1, 2, 3, 4, 5, 6, 7, 8, right? And then times n plus 1, which is 15 plus 1, which is 16, over 12. And that is 8.64. That's what that is. And people are always surprised that it's this 12, no matter how big your sample size is. So if you'd like me to show you where that 12 comes from, I can, but let's just first get through this problem, okay? Does that sound good? So here we have this. So we have observed minus expected over our standard error. That's our usual. And that's over 8.64. And what is that? It's a very small number, 0.058. So that's our z-score. All right? And so now, mark it on the normal curve and calculate the p. So let's just remember what we're doing. We've done this so many times before. On a z-curve right here, we're saying that this rank sum is distributed as a z-score, which is 0 in the middle like this, -1, -2, and -3. I mean, if we wanted to match up the axes with our rank sum for group A, rank sum, our expected value is right in the middle, which is 56. And we want to know where to place 56.5. Is it here? Is it here? Where is it? Well, it turns out that 56.5 is so tiny. It's just really tiny. I can't even draw it small enough so you'll see it, but here, I'll just make it, pretend it was like that. That's where our z is, right there. That's where 56.5 is once we change it to a z-score. So this is 56.5 right there. Okay? So we want to look at the p-value, the area of the tail, or is it two tails? It's giant. So what's this saying is if the null was true and there was just a random, I just gave, if they really were all the same test or equivalent test completely, and I handed 7 of them randomly one test and got these scores, and the other 8 that and got the scores, basically, it's about as close to showing that they're from the same distribution as possible, right? Because you expect to get 0, but you're not going to get exact. So I was delighted if I saw something like this, because I would say, wow, they really are from the same distribution. So remember, this is the distribution. If this is the distribution of our test statistic, this is the probability of seeing, well, why don't we get the p-value here, between between z and negative z. So between this and negative 0.058, our middle area, we'd look that up. I mean, we don't have to be so exact. We know that we're not going to get a p-value less than 5%. Our p-value, and we didn't make a hypothesis that do not come from the same, there's no direction there, so it's always two-sided. There's no direction there. Look at this p. It's giant. It's impossible to get anything bigger than this unless you got exactly 0. That is our p-value. So we just want the middle area. If you really want to go through this, okay, so the middle area is 0.05, about 4. We have 0.058, it's about 4%. So our p-value is equal to 100 minus 4%, which is equal to 96%. That is a huge p-value. Conclusion? Well, conclusion is obviously the null seems very good. The null, we assume the null, and it's just tremendous evidence that it is the null. So obviously cannot reject the null. It's as far from rejecting the null as humanly possible, pretty much. So cannot reject the null. We're going to conclude that I'd be delighted that really those exams are of equal difficulty. The two versions come from the same distribution. The two exam forms, the two groups, the two exam forms come from the same distribution. It's about as fair as I can do. That was great. All right, now what would have happened if we had done Z? I said choose one. What if we had done ZB? Let's see what would have happened. If we had done ZB, what would we have gotten? Our observed ZB was what? I'm just doing the same thing. Our observed is right here, 63.5, minus our expected. We haven't done the expected. What would our expected value for RB be? It would just be NB, right? Instead of over, I don't have to write all that out. It's just going to be NB here. So it would be 8 times the average, which is 64. Right? The only difference would be, you'd put a B in there. So it would be the sample size here. So it's 64. So minus 64. And now they have the same standard error of 8.64. So look what happens. Instead of being 0.5 above, it's 0.5 below. So it would be negative 0.5 over 8.64, which is negative 0.058. It would be right here. So we can draw our B below, just to show you. Our B has 64 in the middle, and its expected value is 64, and our observed value is always just going to be the so there here we have 0.058 for one of them, and it'll just be the opposite. So that's 63.5. So that's our observed, and that's our expected, and this is our observed and our expected. So it gives you, to sum up, they're going to be opposites, which means they'll have the same p-value. which is what we're interested in. Okay, does that make sense? Questions? Anybody have a question? Anybody want to see this, or should I just show you after class, those who are interested, where that 12 comes from? Or post it? Do you want to see it now, or what would you like? Question? Which, raise your hand if you want to see it now, or want to see if you want to see it after class. You want to, 2 people want to see this now? 3? I can show it to you now. Okay, so basically what we're doing here is what? I just need a piece of paper. Did I not bring a piece of paper? I am so sorry. Does anybody have a piece of paper? Does anybody have one? Sorry. It will just take a second. I'm not going to, I'll just show you where that 12 comes from. Because that's what surprises people. No matter how big the sample size, why do we get that 12? So basically, what are we doing here? We're doing a standard error, right? A standard deviation. So a standard error is, what is it? A standard error for the sum. So a standard error for a sum is the square root of n times the standard deviation of the population it comes from. So this is the part where you're going to get this 12 from. So how are we going to do this? Remember that the standard deviation, we're looking at numbers between 1 and n here, right? So in this case between 1 and 15, but between 1 and n. So the standard deviation, we can do the variance. The standard so the standard deviation squared, the variance, is equal to what? What would it be? The sum from, it's actually easiest to do from I is equal to 0 to n. And then you can add the plus 1 in later. So from I is equal to 0 to n of, remember you take each number and you minus the mean and square it. That's the sum of the square deviations over n. And then to get the square root, you just take this, to get the SD, you just take the square root of that. So that's our variance. So now we have that, and what are we going to do? Well, the computational formula, I could go through it if you want, but the computational formula for this that you might have seen elsewhere is from 0 to n of x sub I squared over n minus x bar squared. And this is really easy to show algebraically. Okay? Those, just another way, just simplifies to that. Okay, so now, what are we going to do? So I think the easiest thing to do would be to do it in the continuous case. If you want to see this discrete case, it's harder, and I can show you it's harder to do. But if you do it in the continuous case, then you would just take the integral from 0 to n of x squared over n, right? Minus the mean is going to just be n over 2 squared, right? So we'll just evaluate this integral, which is x cubed over 3n. We'll evaluate that from 0 to n minus n squared over 4. So when you evaluate that from 0 to n, what do you get? You get n cubed over 3n minus 0 minus n squared over 4. So that's n squared, right? Cancel out the n's, over 3 minus n squared is so easy, over 4, which is n squared over 12. So this is where that 12 comes from. And so it comes up all the time. And you'll see this 12 when you take integral of numbers between 0 and n, basically. So that's the idea, and it doesn't depend. So now what did we want to do? We wanted to go back and plug it in. It gets a little more complicated, because if you want to plug it in here, the standard error of the sum is equal to the square root of n times the times SD. So you'd have to take the square root of that, which would be times n over the square root of 12. This formula works with replacement, and we're doing without replacement, so it doesn't really, this isn't exactly what you get. You get, well, the n plus 1 comes from, because we go from 1 to n, so that's explained. The 12's explained. But this here, I'd have to, it's a little more complicated to explain the exact formula, but there's where the 12 comes from. Because remember, we're sampling without replacement here. We're dividing it, so we'd have to use the correction factor, and then we'd have to, it's more complicated. But that's where the 12 comes from, okay? If you want to see the exact reasoning, it's, I'll post a link to it, the exact derivation, and for the discrete case. Okay, so that's pretty much it, and hopefully you'll remember the 12 now. All right, let's move on. Now, whoever gave me the piece of paper can have that. Yeah, you can take that. Okay, so now, a variation on this rank sum is something called the U statistic. And I like it better, and it's used, one reason I like it better is because all the tables, if you don't have a big enough sample size to do a normal approximation, you use tables. And all the tables are in terms of U, not in terms of rank sum. So you sort of have to convert anyway from the rank sum to the U. So it's easier for me to just think of it directly as the U. Also, so let's just go through it, and we'll look at this. All right, so we use the U instead of the rank sum, but we're going to get the same exact p-values. All right, so what is the U statistic? It sums the number of times that each member in this group outscores members in that group. So instead, you don't really have to rank them. You can if you want, but you don't. You could just go directly. What am I doing? I'm saying, okay, 11. Pretend there's 2 teams here. There's 2 teams. And pretend each person in this team plays each person in that team. Like if you play tennis, they're all singles matches where this whole team plays that whole team. And their score was going to be all the wins in this team versus all the wins in that team. Okay? So this person has an 11. Lost every match. He's lower than everyone. So he contributes 0 to the team. All right? To his team. 0. So he has a U count of 0. Next person, 70. What does he do? He beats how many people? 1, 2, and tied with 1. So you count ties as a half. So he's got a score of 2.5. Next one, 75. He beats 1, higher than 60s. He has a score of 3. 85 beats 1, 2, 3, 4, 5. 88's the same. Beats the same 5. But 92 gets 6 because he also beats this one. 96 beats everybody, 1, 2, 3, 4, 5, 6, 7. Right? So we can add them all up. And that is the U count, which is 28.5. Okay? Now you can choose one group and add its U counts. That's called the U statistic. That's 28.5. You may choose either group, but I usually choose the group with the smaller number of observations. So that's what I did. And this one's determined. You could go ahead and count it if you want, but it's determined. How is it determined? Think about it. The total has to be what? I say it right here. The total has to be the number in this group times the number in that group, which is 56. Because there's 656 total pairwise comparisons. Think about it. We're looking at how many times there's 7, this person plays 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 comparisons, plus another 8 comparisons, plus another 8, plus another, plus another. So that's 7 times 8. It's like, how many total matches are there? If every single person plays, every single person on this team, there's 7 times 8 matches, 7 times 8 games, 56 games, and then you just count up how many one team won versus how many the other team won of the 56 games. So this one has to be 56. The two have to sum to 56. So this should be 27.5, because together they sum to 56. And you can check it to make sure that your arithmetic's correct. Okay? This has to sum. This has to equal. Does it equal? Well, first let's do it. Okay, so 60. Do you want to do it just to get some practice? I'll give you a minute to do it, or a few minutes, and then just write down what it is. Just because if you just write down what I'm doing, you might forget how to do it. This one's really easy. 100 beat everybody, so he has to have a score of 7. Because there's 7 people here. And this one, 60 just beat 11, so that's 1. Okay, so here's 60 was 1. I'll just write them down, see if you got the same thing. 65, this is 1.5. 70 beats 1.5. Is that what people got? That everybody got? And when you add them up, you should get 27.5. And make sure that these two add up to what? 7 times 8. And they do. All right. So, by the way, if you already have these ranks, we're doing the same thing. All we're doing is once you already have these ranks, you're just testing. Like number 11, 1, is it bigger than any of these numbers? No, rank of 0. So he got a U count of 0. Everyone beat him. The next one, 74.5. Okay, so that means, what is he? That he's bigger than 2 numbers and tied with 1. So that's where the 2.5 comes from. 6. How many numbers is it bigger than? 1, 2, and 3 numbers. So that's the 3, etc. But I think it's just easier to do this. I just think this is easier because you don't have to put them in ranks. You can just look at one group and do it. All right, so now we can do exactly the same thing. Now, what's the expected value of the UA and the UB? Well, they're the same. They're the same. And what they are is if you think half the matches would go to one team and half would go to the other. Even if there's only one player on this team, you'd expect they'd be in the middle of the pack and would, beat 4 of the people and lose to 4 of the people. So you'd expect it's going to be, and it's going to just be, for all of them, you'd expect that they'd be, half the matches would go to one team and half to the other if you're just randomly sampling, dividing them into two groups. You wouldn't expect all the worst players on one team and all the best. You'd expect them to average out to be the same. So that's what this is. So your expected value, no matter what your sample size, that's an advantage too, because the other one depends on your sample size. But this just says the total matches won by the two teams is going to be the same. It doesn't depend on the sample size. And the standard error is exactly the same as before because we're going to get exactly the same thing. 7 times 8, it's the same formula, times 16 over 12, which is 8.64. And why is it the same? Well, it's not a surprise because they really just differ by this constant here. Look, when group A has all the lowest numbers, what is its U statistic? If all 7 of the lowest numbers were here, they'd have a rank of 1, 2, 3, 4, 5, 6, 7, and they wouldn't win any matches if they're all worse than the next team. So it would have a UA of 0, and its rank would just be the numbers from 1 to however many, what the sample size was. So basically, they just differ by that constant. They just differ by a constant. We can check that. UA right here is what? UA, and then you could, it's going to be equal to that plus RA. Let's see. Do you think that's? I think that's right. 20. What was UA's 28.5 plus? If you add the numbers 1 through 7, you'll get 7 times 8 over 2. And that should be equal to what RA was. Whatever RA was, 56.5. Is that right? 28.5 plus 28 is 56. Yep, that's right. So it does work. Okay. And now what are we going to do? So, all right, so we can calculate a z-score. And can you see it's going to be exactly the same as before? So our observed minus our expected is 0.5 still. So we're going to have 0.5 over the same standard error. So we're going to have the same thing. We can just do it 28.5 minus 28. That's that 0.5 over our same standard error. And that's going to give us the same exact z-score. All right, so we can mark it here. Here we have a z. And as a U statistic, right in the middle is half the matches, which is 28. 7 times 8 over 2. And we got 28. We got that. So 28.5 are observed. Here's our expected value of UA. Our observed is just 0.5 away. But 0.5 away turns out to be really, in terms of a z-score, it's super close. So right there is 28.5, and that's our observed. Observed minus expected was 0.5. But once we put in z-scores, it's z equals 0.058. So we're going to get exactly the 4% in there. Exactly the same thing. All right, so we get same, 96%. And conclusion, of course, is cannot reject the null. Overwhelming evidence that the two are from the same distribution. All right, compare the ZB to the ZA. Compare the p-values. Okay, so we can. How would UB be? This is even easier because they have the same expected value, right? I don't have to put them on different. They have the same expected value. I don't have to do anything differently here. Okay, so UB, this is the expected value for UA, and it's also the expected value for UB, for both of them. So they're just both on the same distribution, and what is, we want to do ZB, what do we have? 27.5, our observed value, 27.5 minus our expected of 28 over that same standard error is just negative. So it's right, it's this one. That's 27.5, and we get, this is equal to a negative 0.058, so it's right here, negative 0.058. So it's the same thing. Okay? So they yield exactly the same, ZA is equal to the opposite of ZB again, and the same p-values. And it's all the same as with the rank, as with the R, Ranksum, Z and p-values. Exactly the same. I should say exactly the same. That's just what I said here. All right, and same p-values. Any questions? It's pretty simple. I like this stuff. Now, let's say you have small sample sizes. How do you use the tables? So I said the tables are always in terms of the U statistic that I've seen, most of them, and always in terms of the smaller U. You could make it in terms of the bigger U, but they usually make it in terms of the smaller U. So our smaller U, if we wanted to look at a table for this, I mean, it would be crazy too, because we know it's so close, but we'd look at 28.5 or 27.5. We'd choose the smaller one, and we'd say, okay, this smaller one, 27, is it so far down here, so far from what we'd expect that the p-value is less than 5%. We know it's not using the normal curve. We can use the exact probability distributions. What this is that these are small enough sample sizes that you can calculate, and they have tables for the exact probability, for the critical values here, the cutoff values at 5%. So that's what this is. So this right here is, what is this? These are the U star values. Okay? So this table gives you U critical values at alpha equals 0.05% for the smaller U stats. That means you have to have a critical value less than that, further away from the middle, less. So you want to check, where does it say that? Okay. So your observed has to be less than, farther away from the middle, less than. If we were doing the bigger one, it would have to be bigger than. So you want less than these values. So how do we read this table? N2, that N1 and N2 is our sample sizes of the two groups. So this is the small sample size for the smaller group. So that would be 7 for us right here. And this is the sample size for the larger group. Our larger group had 8. Don't confuse that with larger U statistics. So this is just where to look here. So we're looking right here at this, our critical value. So this is the sample size for this larger group. Okay, so that's our critical value. So your observed U, the smaller one, which is what? Our observed U, our smaller U is equal to, well, they're so close together, but this is the smaller one, 27.5. So you have to ask yourself, is our smaller U less than or equal to 10? No. So we cannot reject the null. It'd have to be smaller, that would have to be really extreme down. No, so cannot reject the null. And we knew that. Now, any questions on that? Now, let's rearrange these scores so we could reject the null. Well, if all these scores, let's rearrange them. Rearrange the scores to find the U-stat closest. Let's find the smallest one. First, closest. Rearrange the scores to find the, first we'll do part A, smallest. We'll do A. Do the same thing, but to find the U-stat smallest. Not closest to find smallest U-stat. That's real easy. This will be part, and then we can do part A later. So E, to find the smallest U-stat, what would we do? Wouldn't we rearrange them to have what? The 7 smallest numbers, right? So we'd say 11, 60, 65, the 2 70s, right? 1, 2, 3, 4, 5. 75 is the next one, and what would be the next one? 79? So that would be group A. 3, 4, 5, 6, 7. So what would be its U count? Do any of these beat any of those? Do they? What would be its U count? 11, 0. Didn't beat any of them. 60, didn't. These would be different. I'd have to make group. So this is group A with 7, 1, 2, 3, 4, 5, 6, 7. And then group B would have to be the other ones. So you'd have to say 79. What comes after 79? 81, then 85, then 88, then 90, 92, 1, 2, 3, 4, 5. 3 more numbers. What are they? 95, 6, yeah. 95, 96, and 100. Okay? Now you can see it. This would have a U count of 0, because it doesn't beat any of those. They'd all have a U count of 0. So this one would have a U count equal to what? They want all the matches. So 7 for this one, plus 7, plus 7, plus 7. So it would be 7 times 8, which is 56. So certainly we'd reject the null, right? That would be the U counts. By the way, what would be the ranks? The rank would be what? 1, 2, 3, 4, and 5. 6 and 7, and the ranks here would be 8, 9, 10, 11, up to 15, right? So this would be your 28, right? And this would be what? It has to add up to 120, right? So this would be 92. But you know what? Do you want to do this one for extra credit or just for fun? Try to, okay, so we got well below it. So it doesn't have to be the 7 lowest scores and the 8 highest scores. But maybe, what would it be? Just play around with it. See if you can find one that gets really close to 10 without going over. And next time we'll look at it. So if anybody comes up with one, just show me at the, just give me a sheet of paper with your name on it and the solution. And we'll look at them next time. I haven't done this, but there's probably a few ways to do it. But this one's really low. And of course, it's going to be significant, but we want to, it doesn't have to be all the lowest ones and all the highest ones. But I think it just helps you understand what's going on if you did that. Questions on that? Questions? All right, so now let us finish up this. So I said we're testing. The null is that, that the two groups come from the same distribution. So a strong point of this, I abbreviate this, and I'm looking at it as weapons of mass, something horrible, instead of Wilcoxon Mann-Whitney test, is that it compares the whole distribution, not simply the means or medians. This means that two distributions could have the same mean or median, but the WMW would reject the null. So let's look at this. Look at the distributions below. In both cases, they have the same mean, but different distributions. Let's think if we get different ranks and U counts for these. All right, what if it's symmetric around the mean like this? They have different distributions, so what would the ranks be? Okay, well, the smallest one is way down here. That's 1. Then the next one, 2. Then the third is, these are both 3 and 4, so that's 3.5. The next one, you can think of just fitting these right in here. The next one is, what, 3 and 5. So the next one, this one right here, what rank is that? That's we have 1, 2, 3, and 4, and I gave them both 3.5. And now I just have these last two to do. This one, of course, is the biggest of the 6, and that is 5. All right, so there is our ranks. And if we add them up, what do we get? We get 10.5, and this is 10.5. They're the same. Did I do that right? Let's see. We want to check, just to make sure, what should it be? The 10.5 plus 10.5 should be equal to 6.7, 6 times 7 over 2. Right? N times n plus 1 over 2. And it is. That's 21 and 21. Okay, we did it right. Now let's do the counts. Now, if we're doing the counts, we can say -1, this beats what? -2, and that's it, 1. 0 beats 1, that's 1.5, and 1 is, it beats 2 of them, this and this one. So we get 1 plus 1.5 plus 2 is equal to 4.5. And what do we get when we do these? -2 doesn't beat anybody. -2 doesn't beat anybody. 0 is 1.5. And 2 beats everybody, right? 3, excuse me, 2 right here beats all 3 of them. So that's 4.5. And just to make sure we did it right, 4.5 plus 4.5 should equal what? 3 times 3, and it does, so it checks out. So this, when it's symmetric around the mean, would it detect the difference? No. So it doesn't in certain cases. What I'm trying to say is that it's not always, even though it's testing, whether it's not foolproof. Here, it does. We can quickly do this one. Let's just do the U counts because it's easier. So the U counts right here, we have 1, 1, and 1. All three of these just beat negative. You can place all three of these right in here, and you can see they just beat this one. They line up, right? And these both, this one is 0, and these two beat all three of those. So we get 1 plus 1 plus 1 equals 3, and here we get 6. And 6 plus 3 equals 9, and here it would detect it. So this is yes. So the lesson is, in general, that when means and medians are the same, either one or both of them, when means and medians are the same in the two groups, these tests will miss distributions that are different when they're symmetric around the mean. So they won't detect differences in distributions that are symmetric around the mean. So they have some failings, but not very many. These are really popular tests, so it's important. It's very useful to understand them. But and they won't always if they're asymmetric, but usually. So a lot of intro stats classes don't teach these non-parametric tests, but they're being used a whole lot, and so I think it's useful to understand them. And we're going to finish up, and we're going to look at, now once you understand this one, they all work the same way. So we're going to fly through the next, look, it's only 2 sides. So next time, look, we're just going to do these 2 tests, and then I'll show you what you have to study for the final, and which is just exam 3. Okay, take care. Bye.